Welcome to another session of differential geometry. Today we are going to deal about parallel vector fields. So the parallel vector fields means we are having two types of parallelism here. One is going to be Euclidean parallel and another one we will say that this is just parallel. So remark. Last class we have studied about covariant derivatives and we have seen that the covariant derivative actually gives naturally the concept of parallelism on an n surface. So the covariant derivative leads naturally to the concept of parallelism on an n surface. Next definition is we are going to deal about the parallelism. As I said, two types of parallelism we are going to deal. One is going to be Euclidean parallel, another one is Levi Civita parallelism. Definition: in Rn plus 1, the vectors v equal to pv which belongs to Rp n plus 1 and w is equal to another vector field. I'm considering this w is equal to some qw which also belongs to Rq n plus 1. We said are said to be Euclidean parallel if this v is equal to w. That means suppose you have got 2 points over here, p and q, and here you have got a vector as v, then this vector is also having the same measurement and same direction. Okay, length also same, direction also same. Then we will say that v and w are Euclidean parallel. Next definition. Hope you understand what is Euclidean parallel. A vector field X along a parameterized curve alpha from I to Rn plus 1 is Euclidean parallel if x of t1 equal to x of t2 for all t1 t2 belongs to I, where x of t is equal to alpha of t comma alpha of t comma x of t for t belongs to I. So whenever we are dealing with vector fields, we will say that a vector field along a parameterized curve alpha is Euclidean parallel whenever x of t1 equal to x of t2 for all t1 t2 belongs to I. So this is the condition, x of t1 equal to x of t2. This actually implies that this x of t1 equal to x of t2 associative function for every t1 t2 belongs to I. So this is also true. Thus what is follows is whenever we say that Euclidean parallel means its covariant derivative should be 0. Thus what is the reason? See, here is given that x of t1 equal to x of t2 for all t1 t2 belongs to I. That means this x of t1 is going to be a constant one. So when you are finding its derivative means it should be 0. So thus x is Euclidean parallel along alpha if and only if the condition is x dot is equal to derivative is equal to 0. So thus x is Euclidean parallel along alpha if and only if our condition is its derivative is 0. Okay, next definition is what is Levi Civita parallelism? Next definition, let capital S be a n surface in Rn plus 1 and a parameterized curve alpha from I to S, a smooth vector field x tangent to S along alpha is said to be Levi Civita parallel or simply parallel if its covariant derivative, that is x dash, equal to 0. So what is Levisivita parallelism? We have got a surface S in Rn plus 1 and a parameterized curve alpha from I to S. Now a smooth vector field x tangent to S along alpha is said to be Levi-Civita parallel or simply parallel if x dash equal to 0. That is covariant derivative is 0. So what's the meaning of that? That means the vector field should be a constant one, right? So thus x is parallel along alpha. X is parallel along alpha if this x is a constant X is a constant vector field along alpha as seen from. So when you are seeing from S, the vector field whatever given should be a constant one. Then we can say that that is Levi-Civita parallel. Next we are going to deal about some properties of Levi-Civita parallelism. Properties. Properties of Levi-Civita parallelism. We're going to deal about 5 properties of Levi-Civita parallelism. The first property is if X is parallel along alpha, X is parallel along alpha, then X has constant length. X has constant length. That is, we're having since d by dt of norm of x square. Okay, so norm of x, we want to say that norm of x is going to be a constant one. So we're considering d by dt of norm of x square, and we want to prove that this is equal to 0, right? So this is equal to d by dt of x dot x, right? Now this is equal to, when you are finding by using product rule, you will get this to be equal to 2 times x dash x, and this is equal to 0. What's the reason? Since it is parallel, given Levi-Civita parallel, so x dash should be equal to 0. Therefore, this value equal to 0. So that means, which implies the norm of x is a constant one. That means it's of constant length. So proof is very simple one. So first property is if x is parallel along alpha, then x has a constant length. Second one, if x and y are two parallel vector fields, if x and y are two parallel vector fields along alpha, then x dot y is constant along alpha. X dot y is constant along alpha. Since this reason, since x dot y of dash, when you're finding, this should be equal to, by our formula, x dash dot y plus x dot y dash. But given that it's parallel, x and y are two parallel vector fields, so x dash should be equal to 0 and y dash also should be equal to 0. So this is equal to 0 since x dash equal to y dash equal to 0. And third property, Third property is if x and y are parallel along alpha, if x and y are parallel along alpha, then the angle between x and y, that we can write it as cos inverse of x dot y by norm of x into norm of y. Cos inverse of this between x and y is constant. Between x and y is constant along alpha. Is constant along alpha. So we want to have since x and y are constant given, right? X and y are constant is given one. So what about x dot y is again constant by our second property. Then by property 1 and 2, property 1 and 2, we have x dot y is a constant and norm of x and norm of y are again constants. So what you're having is a constant term by a constant term and cos inverse of that term. So again that will result a constant one. Okay, so therefore cos inverse of x dot y by norm of x into norm of y is a constant. So we have proved three properties, and fourth property is going to be if x and y are parallel along alpha, if x and y are parallel along alpha, x and y are parallel along alpha, so x dash equal to y dash, that's equal to 0, right? So I'm writing so x dash equal to y dash equal to 0, since it's given that x and y are parallel along alpha. Then so are x plus y, and cx for every constant c belongs to the real numbers. So here what we are having is we want to prove that these are parallel. That means x plus y dash, this equal to 0 we want to prove, but we know that this is nothing but x dash plus y dash. Now this equal to 0 plus 0, that's equal to 0. Again we are having cx dash. Cx dash is nothing but c into x dash, that is c into 0. Again that will result 0, right? So we can have this in bracket So this is the reason why we are saying that whenever x and y are parallel along alpha, so are x plus y and cx. And the fifth property, the velocity vector field, the velocity vector field along a parameterized curve, along a parameterized curve, velocity vector field along a parameterized curve alpha in S is parallel if and only if alpha is a geodesic. Alpha is a geodesic. So what this means is the velocity vector field along a parameterized curve alpha in S is parallel, that is Levi-Civita parallel, if and only if alpha is a geodesic. So how to prove this? For velocity vector, vector alpha dot is parallel. So this implies your alpha dot dash equal to 0, right? So alpha dot dash equal to 0, which implies what is alpha dot dash? That is alpha double dot minus alpha double dot n of alpha of t, that is n composition alpha times n composition alpha. So this equal to 0, right? So this implies alpha double dot is equal to some value will be here, that is some scalar value alpha double dot n dot alpha times n composition alpha. That means this is a multiple of n, right? The normal one. Or this implies alpha double dot belongs to S of alpha of t perp. So what is the meaning of that? This means that alpha is a geodesic. This implies alpha is a geodesic. Okay. So this is the proof of fifth property. So today we have dealt about what is Euclidean parallel, what is Levi-Civita parallel, and some 5 properties of Levi-Civita parallelism. Next we are having a theorem here. Theorem. Let S be an n surface. Let S be an n surface. S be a n surface in Rn plus 1. Let alpha from I to S be a parameterized curve. Be a parameterized curve in S. Let T naught belongs to I and let V belongs to S of alpha of T naught, then there exists a unique vector field of capital V tangent to S along alpha, S along alpha, which is parallel, which is parallel, and has v of t naught, v of t naught equal to v, v of t naught equal to v. So this means that let S be an n surface in Rn plus 1, and we have got a parameteristic curve alpha, and we are having a vector v belongs to S of alpha of t naught. Then we can find a unique vector field v tangent to S along alpha, and which is parallel and has v of t naught is equal to v. So we want to prove this. So proof. We require a vector field v tangent to S along alpha satisfying v dash equal to 0. That is, we need a vector field v such that this v dash equal to 0, right? But v dash is equal to but v dash is equal to, but it should be v dot minus v dot with n of alpha times n of alpha, right? Now this can be written as v dot minus of v dot n composition alpha dash, I am writing minus v dot n composition alpha dot. While expanding this, you will get a term, extra term like this. So I have deleted, or I have subtracted that term here. That's times n of alpha. So this can be written as v dot plus of v dot n composition alpha dot of n composition alpha. What's the reason? Since given that v is tangent to S and n is perpendicular to S, so v dot n composition alpha term, v dot this term should be 0, right? So since v is tangent to S and n is perpendicular to or orthogonal to S, therefore v dot n composition alpha should be 0, right? So this is the reason we have got only this term. Thus what you're getting is v dash should be 0. Am I right? So this is the term. Thus v dash equal to 0 you will get. Which implies or implied by v satisfies the differential equation v dot plus v dot n composition alpha dot n composition alpha. is equal to 0. Call this as equation 1. Now this is a first order differential equation in V. Now 1 is a first order differential equation in V. If we write V of t equal to alpha of t comma v1 of t comma v2 of t etc. Vn plus 1 of t, then equation 1 become, we have written V in terms of its components. So as per this, we will get n plus 1 equations, right? So equation 1 become 0 equal to first term alpha of t comma dv1t by dt, right, dv2t by dt etc. Last term dvn plus 1 of t by dt. That's the first term, right? This term v dot plus next term should start a bracket. First term is same thing v, so that is alpha of t comma v1t comma v2t etc. Vn plus 1 of t dot alpha of t. Next is the derivative, right, of n composition alpha, d by dt of n1 composition alpha, right, etc. Up to what term will come, etc. up to d by dt of n plus 1, right, n plus 1 composition alpha of t. So here also 1t will be the into n composition alpha of t will be the, so that is equal to into alpha of t comma n1 composition alpha of t etc. Last time n plus 1 composition alpha of t. See, we have converted everything into its components, nothing else. This implies that each component term should be equal to 0. So that is, we can take this as component wise, means that is alpha of t, that is alpha of t comma dv1t by dt, v1t by dt etc. d vn plus 1 of t by dt. So first term plus next term starting v1t into d by dt of n1 composition alpha of t plus etc. plus vn plus 1 t, vn plus 1 t into d by dt of n plus 1 alpha of t, right? Next term into, one more term is there now, into alpha of t, comma, n1 composition alpha of t, etc. n plus 1 composition alpha of t. So this term equal to 0, right? And that means that is alpha of t, that is alpha of t, comma, dv1t by dt, extra dvn plus 1 of t by dt. The term as such, here we are having a dot product here, so plus next term also alpha of t, comma, this dot product we want to write this as dot product now, so I'm writing that as using sigma notation, sigma j equal to 1 to n plus 1, I can write vj of t, into d by dt of nj of d by dt of nj of alpha of t, right? Nj of alpha of t. First term, this into n1 alpha of t. Like that terms will come. So like that, so many terms. What should be the last term? Comma. Last term should be sigma j equal to 1 to n plus 1 vj of t into d by dt of nj of alpha of t into n plus 1 n plus 1 alpha of t. This much of term should be equal to 0, which implies d by dt of vi of t. We are taking one term, one common term, or we can say that one general term from this expression, that is vi of t plus sigma j equal to 1 to n plus 1 vj of t into d by dt of nj of alpha of t, into ni of alpha of t is equal to 0 for I equal to 1, 2, etc. up to n plus 1. Now this implies, we have taken only a general term, so this implies d by dt of vi plus sigma j equal to 1 to n plus 1. I can write this as n1 or ni composition alpha into nj composition alpha dash of Vj equal to 0 for I equal to 1 to etc. up to n plus 1. Right? So this is your equation 2. Then equation 1 is equivalent to the system of first order differential equation 2. Since we have got this from equation 1, we have substituted the components and we have reduced it like this. So then equation 1 is equivalent to the system of first order differential equation 2. So these two equations are going to be the same. Now what we are going to do is, by existence and uniqueness theorem for solution of first order differential equation, we will get there exists a unique vector field V. So by the existence and uniqueness of solution of first order differential equation, there exists a unique vector field V along alpha satisfying equation 1 together with the initial condition together with the initial condition V of t equal to small v, right? That is satisfying Vi of t naught equal to Vi for I equal to 1 2 extra up to n plus 1, and V is equal to alpha of t naught comma V1 V2 extra Vn plus 1. So these two. Next we prove that V is tangent to S. So we have got such a vector field over here. Next we want to prove that it is tangent to S. So next we prove that since we want to get such a vector field and we want to prove that this is tangent to S. So we prove that V is tangent to S. Along alpha. We have V dot n composition alpha dash is equal to V dot composition n composition alpha plus V dot n composition alpha dot So this is equal to minus of, we have got this term previously, so minus of V dot n composition alpha dot, right, one term, times n composition alpha dot with n composition alpha plus v dot n composition alpha dot. From where you got this? By equation 1. Now this is equal to minus of v dot uh, n composition alpha dot plus v dot n composition alpha dot, right? So this will result 0. Hence what you can conclude is, hence v dot n composition alpha is constant along alpha, is constant along alpha. But what you're having is v dot n composition alpha of t naught, that's equal to is nothing but v of t naught into n of alpha of t naught, right? Now this is nothing but v of t naught is small v, right? So v dot n composition alpha of t naught, this is equal to 0 because this v belongs to the tangent space, right? So this is equal to 0 since v belongs to S of alpha of t, tangent space, and this is normal space. So that dot product should be 0. So what you're having is, so v composition or v dot n composition alpha is equal to 0 along alpha. So v is tangent to S. So v is, see, this plus normal component, that is 0 means these two are orthogonal, right? So v is orthogonal to the normal, that means v is tangent to S. V is tangent to S along alpha. Finally, this vector field v is parallel since it is satisfy equation 1. Now finally this vector field v is parallel since it satisfy equation 1. What was equation 1? This was equation 1, right? That is v dot equal to 0. So v dash equal to 0 we will get. So this means that this is parallel. So today we have proved the theorem that if S is an n surface in Rn plus 1 and let alpha from I to S be a parameterized curve, then T naught belongs to I and V belongs to S of alpha of T naught, then there exists a unique vector field V tangent to S along alpha which is parallel and has V of T naught equal to V. Okay, so hope you understood today's class. If you find any difficulty in understanding this theorem and all, just be free to ask me. So I'm winding up today's session here. Thank you for your patient listening. Thank you.